Hi, folks. How's it going? We're covering section 1.4 today, which is further adventures in row reduction. Let's go ahead and get started. All right. So we've been talking about echelon form, um, and it can be the case that a matrix is in echelon form, even though some columns don't have a leading entry. Um, So in the example here, we have matrices that are in echelon form. I've circled their leading entries, and this column doesn't have one um, because the leading entry is based on the row, and this row doesn't happen to contain any leading entry. That's perfectly okay, but it does mean something. Um, and so this column is another example of a column that doesn't have a leading entry. We're going to define a column that does contain a leading entry to be a basic column, and a column that doesn't contain a leading entry to be a free column. So basic means it does contain a leading entry. Free means it does not. So in this example, columns 1, 3, and 4 are basic, and columns 2 and 5 are free. So in this example, which columns are basic and free? I don't think it is going to surprise anybody to find that 1, 2, and 4 are basic, and 3 is free. Will every matrix have a free column? Well, no. We've seen plenty of examples already that don't have a free column. 1, 2, 3, 0, 4, 5, 0, 0, 6 is an example where my leading entries show up in every column. Every column is basic. Any variable in a system of leading equations that corresponds to a column with a leading entry is called a basic variable. And any variable in a system that corresponds to a column that doesn't have a leading entry is called a free variable. So we can talk about the columns being basic and free. We can also talk about the variables being basic and free. Let me show you an example here. I have this system of equations here. And this is the augmented matrix for the system. The top row is 1, 3, negative 1, 0. Then the second row is 4, 1, 7, 11. And the bottom row is 2, 0, 4, 6. If we row reduce this, when we say that something is row equivalent, that means these things, these matrices have been, the second matrix is a row reduced version of the first. This just means that row reduction has taken place. Has occurred. And in the process of row reducing, we find that in the echelon form, there is no leading entry in the bottom row. And that means that the third column is free, but that column corresponds to this variable. And so we can also tell you that the variable x3 is free. And in fact, that's what you'll hear more often, is that they hear that the variable is free and not the column. Okay? So let's move on, see where this is leading us to. If the last column of the augmented matrix system is basic, then the system has no solutions. We're going to see examples of all of these in a little while. If the system has solutions, which based on part one, says that the last column has to be free. And also one of the variables is free. Then the system has an infinite number of solutions. If the system has solutions but all the variables are basic, then the system has only one solution. So I promised we'd see some examples. We're going to do some examples, but I'm going to describe one more definition here. Thought the examples were coming, but no, there's another definition to wait. A matrix is in reduced echelon form if it is in echelon form and meets these additional conditions. These are the additionals to be in reduced echelon form. Every leading entry is a 1, and every leading entry is the only non-zero entry in its column, the sole non-entry zero in its column. So these matrices are in reduced echelon form. My leading entries move left to right. That's echelon form. But furthermore, both leading entries are equal to 1. And the other entries in the column are zeros. And so the ones occupy the columns all by themselves. And so that's what makes this reduced echelon form. This matrix is in reduced echelon form. My leading entries move left to right. That is echelon form. And all the leading entries are 1, and the ones occupy the columns all by themselves. That is reduced echelon form. Any matrix that's already in echelon form can be converted into reduced echelon form using a process called backward phase row reduction. And here's the algorithm. But the idea here is that if I have a matrix that is already in echelon form, these are my leading entries A, B, and C, for example. We start at the bottom. We're working backwards now. So we're going to start with the rightmost leading entry. Use combinations to replace all of the leading entries up here with zeros. Turn this into a 0, turn this into a 0, and then divide this row by whatever this number is to make this leading entry a 1. And so now we'll have this. Sorry. And then we will then take the next rightmost leading entry, which would be this one, and do the same thing. Turn the entry above it into a 0, and then divide this row by B to make it a 1. Then we move backwards. We're moving then back to the first row leading entry. And once we get to the top row, we're done, but otherwise we keep moving backwards. So let's give this a try. This is a matrix that's already in echelon form. We're going to use the backward phase row reduction algorithm to put this into reduced echelon form. Okay, so working backwards, we're going to start with the 2. We're going to clear out its column. Clear the entries above the 2. So if I want to get rid of this entry, I can just take 2 minus 2 is 0. So row 1 minus row 3 is going to give me 3, 5, 0, and 6 minus negative 8 is 14. And then the other rows stay the same. Then to clear out this 1, well, there are a couple of ways we can do this, but we could double row 2 and then subtract row 3. 2 row 2 minus row 3. So this becomes a 12. 2 minus 2 is 0. 4 minus a negative 8 is also a 12. Now that the column has been cleared out, we're going to change this 2 to a 1 by dividing by row 2, by dividing by 2. So row 3 divided by 2. Now we're going to move backwards to the 12. We are going to, normally we would clear out the 5 first, but 12 and 5, their lowest common multiple is a 60. And so what we're going to do this time is go ahead and simplify this middle row. Take row 2 and divide it by 12. That's going to give me 0, 1, 0, 1, and that's going to be a lot easier to work with. Now we're going to get rid of this 5. So we're going to take row 1 minus 5 times row 2. 5 minus 5 is 0. 14 minus 5 is 9. And now this column has been reduced, and this column has been reduced. We move backwards to this column and divide that row by 3. So we get 1, 0, 0, 3. And now this matrix is in reduced echelon form. All right, let's move on. Every matrix is row equivalent to exactly one matrix in reduced echelon form. What this means is that if you and your friend are both solving the same problem, you could each get your own echelon form. Depending on how you chose to do your row reduction, what linear combinations you chose to use, you could have different echelon forms for your work. But if you then continued on all the way to reduced echelon form, there's only one reduced echelon form. And so reduced echelon form takes a little bit more work, but it gives us a check because the reduced echelon form is unique for every matrix. And so you and your friend could, if you were solving an echelon form, you could get 2 different answers and you could both be right. But if you go all the way to reduced echelon form, then you both have to get the same final answer. All right, let's move on. So let's look at this system of equations. This is an example of what we're going to call an inconsistent system, and we'll see why in just a moment. So I'm going to, first of all, I'm going to take this system of equations and write it as an augmented matrix. 2, -1, -1, 3 in the top row, 1, 3, 1, 1 in the middle row, 0, 7, 3, 7 in the bottom row. We're first going to go forward. We're going to look at the forward phase. That means we are working forwards through the matrix, fixing problems with the leading entries. And this leading entry is the first leading entry to be in the wrong position. It doesn't move to the right. It should be over here. And so we need to change the 1 to a 0. So we'll do that step. We're going to take 2 times the middle row minus the first row. 2 minus 2 is going to give me 0, but then I have to continue that step all the way across. 3 minus -1, I'm sorry, 6 minus -1 is 7. I should do it over here. Double this, 6 minus -1, and then 2 minus -1 is 3, and so on and so forth. And so now we have these leading entries. And the first leading entry that's a problem is now this one. This should be a 0 so that the leading entry is on the right. So I need to clear out that 7. So we can do that by just taking row 3 minus row 2. 7 minus 7 is 0. 3 minus 3 is 0. 7 minus -1 is -8. And now this is in echelon form. That 0 is not a leading entry. The 8 is a leading entry. This is echelon form. But the last column is basic. The bottom row says that 0 times x plus 0 times y plus 0 times z is equal to 8. And this can't happen. And you can't see this because I'm blocking your way. Let me move this out of the way. There we go. That can't happen. That having a leading entry in the augmented column means that the left side of the equation is 0 and the right side of the equation is not 0. And so we say that this equation, this system of equations is inconsistent because it cannot be solved. There is no solution. And when there is no solution, then we don't need to do the backward phase because we already know that there is no answer. So the backward phase is unnecessary because we already know there are no solutions. All right. So let's move on and see a different example. Anytime that we see a row in an augmented matrix like this, where b is not equal to 0, that's impossible to solve. We call this system inconsistent. We just described that. But let's look at this system. Again, I'm going to convert this to an augmented matrix. 3, 4, -1, 1, 2, 1, 1, 9, 1, 1, 0, 2. All of my leading entries are in the first column. That's bad. We want them to move left to right. The first one, because we're moving forward right now, is 2. We're going to get rid of that 2, make it into a 0, so that the leading entry is going to be here. So to get a 2 into a 0, the lowest common multiple of 3 and 2 is 6. I'll multiply the second row by 3 to get 6. I'll multiply the first row by -2 to get -6. And that changes this into a 0. When we do this all the way across, 3 times 1 minus 2 times 4 is 3 minus 8, which is -5. Then 3 times 1 minus 2 times -1 is 5. And 3 times 9 minus 2 times 1 is 25. Okay? All right. I've gone ahead and done the next step, which is to go ahead and move this entry over to the right. And now my leading entries are here. I need to do one more reduction step to get rid of this -1. So my leading entry goes here. When I do that, my bottom row drops out. I get the equation that 0 equals 0, which is okay. This entry is fine. So now when I'm looking at my system, I have only 2 leading entries. We have the last column is free, but this column is also free. When we have a free variable, then we have more than one solution. And when we have more than one solution, the backward phase is helpful in finding those solutions. So now we're going to work backwards. We're going to take the last leading entry, which is the -5, and what are the 2 things that we have to do to make this into reduced echelon form? We're going to have to clear the 4 that's above it, and we have to change the -5 into a 1. So let's go on and move this. Let's look at the backward phase. First, I'm going to take this row and divide it by -5. That's going to make this into a 1. And then I'm going to take row 1 minus 4 times row 2. So the 4 minus 4 times 1 gives me 0. And then I have to do this step all the way across the matrix. So this becomes a 3. This becomes a 21. And this column is now fully reduced. The leading entry is a 1, and it's in the column all by itself. So I move backwards to this leading entry, and I'm going to divide it by 3. When I divide this by 3, I get 1017, and now this matrix is in reduced echelon form. All right. On the next slide, I'm going to put this reduced echelon form by itself. I'm going to get rid of all this other scratch work. This is our reduced echelon form. What this is saying is that through x1, not x1, x plus z is equal to 7, and y minus z is equal to -5, and z itself has no leading entry, which means z is free. When z is free, that means we can choose any value we want to for z and get a solution. So we can choose a value for z. But we're not going to do that just yet. What I'm going to do is I'm going to rewrite this equation so that the basic variables are by themselves. Put the basic variables by themselves. And now I have an equation for x. It's 7 minus z. An equation for y. Y is negative 5 minus z. And again, z is free. So if I pick, for example, if z is equal to 0, then we get x is equal to 7, y is equal to 5, z is equal to 0. And that should check in these equations. Or y is negative 5, not 5. 3 times 7 is 21. 4 times negative 5 is negative 20. 21 minus 20 is 1. 1 minus 0 is 1. So that checks. The second row is 14. 2 times 7 is 14. 14 plus negative 5 is 9. 9 plus 0 is 9. So that checks. And the bottom row, 7 minus 5 is 2. So that checks. But if we pick z equal to 1, well, let's see what happens. Then x is going to be 6. 7 minus 1 is 6. And y is going to be negative 6. And z is going to be 1. And let's check this again. 3 times 6 is 18. 4 times negative 6. 7 minus 1 is 6. Negative 5 minus 1 is negative 6. 3 times 6 is 18. 18 plus... What in the world am I missing? Plus z. Okay, all right, let's back up. Let's stop this recording.